Alrighty, I'm going to do a quick run through of this question, which is a magnetic field question, all based around a solenoid. So let's have a quick look. It's an insulated wire. The solenoid is of length 4 meters as shown. The wire itself is of diameter 0.25 millimeters, and the pipe that it's wound around is 3 centimeters, as we can see here. Each loop just touches the next. So show that the length of wire is approximately 1.5 kilometers. You may assume that the insulation thickness is negligible. All right, so what we need to do here is calculate the number of turns there are by simply dividing our 4 meters by the width of one turn, and then multiply that by the length of each turn, which is just the circumference of the tube. So what I'm doing then, 4 meters, 4.00, divided by 0.25 millimeters, so that's times 10 to the minus 3. That tells me how many turns there are. Then multiply that by pi d, which is the circumference of the tube. The diameter here, 3 centimeters, so 0.03 meters. In questions like this, where it's a show that the length is approximately, really important that you don't just write equals 1.5 kilometers here. That doesn't get you the marks. You have to calculate the exact value. So let me just put that into the calculator. My phone calculator, my trusty phone calculator, leads me astray frequently, but I stick with it. I've got 1.50796 times 10 to the 3, so 1.51 times 10 to the 3 meters. And that should get me all the marks. 3 marks for this, which is kind of interesting. So I'm assuming 1 for that answer, 1 for correctly calculating the number of turns, and 1 for correctly calculating the circumference. Seems a bit generous, but I'm going to go with it. Okay, so again, this is a show that approximately. So what we're going to do is calculate it exactly. The reason they put these in, the reason they have this is so that if you are not able, if you don't know how to do this calculation, that you've still got the correct result that you can use in the later parts of the question. But you should still do an exact calculation, and you should still use your exact answer in the further parts of the question. That's something that students often ask me. Use your exact answer if you have one. Okay, then part B. The first thing we have to do is calculate the resistance of the wire, really, don't we? Oh my goodness, what happened there? Oh my gosh, it's gone completely barmy. So where am I? R equals rho L over A. That's the formula for resistance. Resistivity 1.59 times 10 to the minus 8 ohm meters, times the length 1.51 times 10 to the 3. I will use the exact value from my calculator though. Over the cross-sectional area, which is pi r squared, pi times a half times the diameter was 0.25 millimeters, wasn't it? 0.25 times 10 to the minus 3 squared. So let's see what that gives me. Calculator time. Really, I should have done this in advance and had the exact numbers ready to go, but that's not how I roll, as well, you guys know. 1.51 times 10 to the 3. I'm almost there. Gives me 4.89 times 489 ohms. And then it's Ohm's law, V equals IR, so I equals V over R equals 12 over 489. Which is 2.45 times 10 to the minus 2. amps. You don't have to do the like which is roughly equal to 25 milliamps. There's no requirement for that last bit, but you can if it makes you feel better. What you should absolutely not do is simply leave the calculation and say that is approximately equal to 25 milliamps. That doesn't get you the mark. Always calculate the exact value. Okay, part C, calculate the magnetic field strength inside the solenoid. So our equation for field strength in a solenoid, B equals N, that is the turn density, the number of turns per meter, times I times mu naught. So number of turns per meter, we can calculate, if we go back up here, we can calculate the width of the wire is 0.25 millimeters. So the number of turns we're going to have per meter is just 1 divided by that. 1 meter divided by 0.25 millimeters. Then multiply by the current that we've calculated. Again, use an exact value. Don't use the rounded off value. Use the exact. Times 10 to the minus 2 amps. Multiplied by mu naught, which is still on the formula sheet as 4 pi times 10 to the minus 7. Let's get a value for that. Goodness me. Uh-oh. I think I might have fluffed this. Calculator did a weird thing there. I've got 1.23 times 10 to the minus 4 Tesla, which sounds reasonable. You know, millitesla sound okay, don't they? Not even 0.1 millitesla sounds all right. Tesla's a big unit, always worth bearing that in mind. 1 Tesla field is a very strong field indeed. So 1.23, I'm not going to bother with a recalculation. I'm going to suggest that that is about right. But yeah, if it's wrong, don't be hitting me. Explain whether or not the solenoid could produce a magnetic field of 2 Tesla. You should include a calculation to reinforce your answer. So the calculation I'm going to do here is to calculate what current would be required to produce a 2 Tesla field. Since N and mu naught are constant, so the current required I would be equal to 2 Teslas divided by this answer that I've got. That many times greater than the current that there was, which was 2.45 times 10 to the minus 2. I mean, if you're not comfortable doing it like this, you could just do the direct calculation. You could just go back to here and mu naught and put in 2. You know, it's the same. It's going to get you the same answer. And maybe that's the more sensible way to do it because it's clearer what you're doing then. Let me get a number for that. Uh, 398 amps. 398 amps. This wire has diameter less than millimeter. You know, that is very, very thin wire, isn't it? Indeed. So if you put 398 amps through wire like that, it's going to melt. If you want, you could back that up with a further calculation. You could actually calculate the heat dissipated in the wire as that, because we did calculate the resistance as 489 ohms, didn't we? So we could just R398 squared, multiplied by 489. Yeah, That is a lot. 7.7 times 10 to the 7 watts of heat dissipated. That is a vast amount. So there's no way, so no. I forgot to put the conclusion. So no, the solenoid could not produce that field. It would literally catch fire. Not, you know, that is beast, isn't it? 77 megawatts. that is ferocious. That is a serious, that is pretty robust output, isn't it? 77 megawatts. That's running a small village. Yeah, anyway, that's that. Do feel free, folks, to request questions if you meet an interesting one. This one was requested, that's why I've done it. If you meet an interesting question, you're not sure how to go about it, or the mark scheme doesn't make sense, whatever, you want me to make a little video like this, feel free to request it.